Here's a question that breaks a lot of developers the first time they hit it. You write a simple stop flag. One thread checks it in a loop, another thread sets it to false to end that loop. It compiles, it passes code review, and then on a real multi-core machine it just doesn't work. The loop spins forever. Nothing in the code is wrong in the way you'd expect. There's no typo, no race on a shared list, no obvious bug. The problem is something most of us are never taught directly. What a thread sees of another thread's writes is not guaranteed unless you tell the compiler and the hardware otherwise. That's where the volatile keyword comes in. In this video, we're going deep on what volatile actually does, the mistake almost everyone makes when they assume it does more than that, and exactly when you should reach for it. Let's make the bug concrete. A worker thread runs a loop that checks a boolean called running. A main thread somewhere else sets running to false to signal it should stop. On paper, this looks completely fine. In practice, the worker thread can spin forever, never seeing that the value changed. The reason isn't magic and it isn't a compiler bug, it's the memory model working exactly as specified. Without a rule forcing otherwise, the compiler and the CPU are both free to optimize this field as if no other thread will ever touch it. That includes caching the value in a register or a CPU cache line and never checking main memory again. The bug compiles cleanly, it passes every code review, and it only shows up once you run it under real concurrency on real hardware, which is exactly why it's so easy to ship. Understand why this happens? You need a mental model of where your data actually lives while a program runs. Every CPU core has its own L1 and L2 cache sitting between it and main memory. When the main thread writes running equals false, that write can land in its own core's cache line and stop there. Main memory eventually gets updated, but there's no promise about when. Meanwhile, the worker thread running on a different core has its own cache with its own cached copy of running, still holding true. Each core is free to keep working from its local copy. Without an explicit rule that forces a synchronization point, the two cores can disagree about the value of that single variable indefinitely. This is not a hardware defect. This is normal, expected behavior for ordinary fields, because enforcing strict consistency on every single read and write would be far too slow for code that doesn't need it. Let's trace exactly what goes wrong between these two threads. The main thread writes running equals false. That write updates its own cache line. The worker thread in its loop only ever checks its own cached copy. It never had any reason to ask main memory directly because nothing told it that this field could change from outside. So the worker keeps reading true forever, completely unaware that anything happened elsewhere. There's no message passed, no synchronization, no handshake between these two threads. The write on one side and the read on the other are simply disconnected. This is the visibility problem in its purest form. The data race here doesn't corrupt memory or crash the program. It just quietly produces a different result than the one you assumed you'd written. This is exactly the gap volatile closes. Mark a field volatile and the compiler and runtime agree to two specific rules. First, every write to that field goes straight through to main memory. It cannot stay parked in a cache line invisible to other threads. Second, every read of that field comes straight from main memory. It can never be served from a stale cached copy sitting in a register or a core's local cache. One keyword, two guarantees applied consistently every single time that field is touched by any thread. Notice what's deliberately not in that list. There's nothing here yet about combining a read and a write safely, and there's nothing about atomicity. Volatile is purely a visibility guarantee, which is exactly the gap that was breaking our stop flag example, and exactly why adding it there fixes the loop. The formal name for what volatile gives you is a happens-before relationship, and it's worth understanding precisely because it's stronger than just a visibility hint, it's an ordering guarantee. The Java memory model says this: if a write to a volatile field happens before a later read of that same field by another thread, then everything that thread 1 wrote before that volatile write becomes visible to thread 2 once it performs that volatile read. So in a writer thread, you could write a plain field, then write a volatile flag. In a reader thread, once it reads that volatile flag and sees the new value, it's also guaranteed to see the plain field write that happened earlier, even though that plain field was never itself volatile. The volatile write and the volatile read act like a synchronization point that drags everything before it along for the ride. Here's the mistake that catches developers even after they understand all of this. Volatile gives you visibility. Does not give you atomicity. Take a shared counter declared as volatile int and have two threads both execute counter plus plus. That single line is actually 3 separate steps. Read the current value, add 1, write the new value back. Volatile guarantees each of those individual reads and writes goes through main memory correctly. It does nothing to stop two threads from interleaving those 3 steps. Thread A reads 0, thread B reads 0 before it has written anything back. Both add 1. Both write back 1, you expected the counter to end at 2. It ends at 1 and you've silently lost an update with volatile applied correctly the entire time. This is the single most common volatile-related bug in production code, and it happens precisely because the keyword sounds like it should solve more than it does. So where does volatile genuinely earn its place? The pattern across every good use case is the same: a single writer, and one or more readers who only need to observe a value, never combine a read with a write. A shutdown flag fits perfectly. One thread sets it once, every other thread only ever reads it. Double-checked locking on a lazily initialized field uses volatile to stop one thread from seeing a half-constructed object due to instruction reordering. A status or configuration field that's published by one writer and polled by many readers fits the same shape: instant visibility, no locking overhead, because nobody is doing a combined read-modify-write. If you can describe your use case as one thread publishes, others observe, volatile is very likely the right and the lightest weight tool for the job. For anything beyond simple publish and observe, you have two heavier but more capable tools. Synchronized blocks give you both visibility and full mutual exclusion, at the cost of threads blocking while they wait their turn, the right choice for compound invariance where multiple fields have to update together consistently. AtomicInteger and its relatives give you visibility plus atomicity for simple counters and accumulators, using lock-free hardware instructions instead of blocking, but without the freedom to protect more than one variable's update at a time. Volatile remains the lightest option of the three, with visibility but no exclusivity and no atomicity, ideal for flags and single-writer state. Picking correctly between these three options means asking one question first: does correctness ever depend on a read and a write happening together as one atomic unit? If yes, volatile alone is the wrong tool no matter how convenient it looks in the moment. Thanks for watching.